Welcome to Ask and Learn.
We are given a subset of the set of strings on an alphabet, and we're asked to prove or disprove statements about this subset. So in part A, we're given the statement, the subset A is a subset of A squared. So the concatenation of elements of A with other elements of A. We see that in fact, this statement is not always true. It's going to be false. And to see why, consider the counterexample. A equals the set containing the string 1, 0. Then it follows that A squared is going to contain the strings 1, 0, 1, 0. But then it follows that 1, 0 is not contained in A squared, and therefore A is not a subset of A squared. Now in part B, we're given the statement, if A is equal to A squared, then the empty string is an A. If the statement is not true, consider the counterexample where the subset A is the empty set. This is a very special counterexample. Well, then it follows that A squared this is the concatenation of all the strings in A with other strings in A, is going to be, again, the empty set. And so it follows that A is equal to A squared. However, because the empty set contains no elements, it follows that the empty set does not contain the empty string, and therefore A does not contain the empty string. In part C, we're given the statement, A concatenation of A and lambda is equal to A. This statement is actually true. To see why, notice that the concatenation of A and lambda is the set of all strings x, y, where x is in A and y is in the set containing the empty string. And so this is the same as the set of all strings x lambda, where x is in A, which is the same as the set of all strings x, where x is in A, which is the same as A. which is what we wanted to prove. In part D, we're given the statement, the clean closure of the clean closure of A is the clean closure of A. So by definition, we see that the clean closure of the clean closure of A is equal to the union from k equals 0 to positive infinity of the clean closure of A to the kth power, so concatenated k times, now we see that the clean closure of A squared, this is going to be the set of all strings xy such that x is in the clean closure of A and y is in the clean closure of A. Now, we know that the clean closure of A is going to contain the concatenation of any amount of strings in A. So it will also contain the concatenation xy when x is an A star and y is an A star. And so it follows that this is equal to the set of all strings z such that z is in the clean closure of A, which is simply equal to the clean closure of A. Now, let's suppose the clean closure of A to the nth power, so the concatenation n times, is equal to the clean closure of A for some n greater than or equal to 2. Well, in fact, we have that then the clean closure of A to the n plus first power, this is going to be, by definition, the clean closure of A to the nth power concatenated with the clean closure of A. And we know by our assumption for the induction hypothesis that the clean closure of A to the nth power is equal to the clean closure of A, so we get the clean closure of A concatenated with the clean closure of A. This is the same as the clean closure of A squared, which we already showed is the same as the clean closure of A. So it follows that the clean closure of A to the nth power is going to be equal to the clean closure of A for all n greater than or equal to, and we showed it was true for 2. Of course, it's going to be true for 1 and for 0, since the clean closure of A to the 0th power is going to be the empty string this is simply for n greater than or equal to 1, and of course we have the clean closure of A to the 0th power is the empty string, or really the set containing the empty string. Now we know that the empty string is of course going to be contained in the clean closure of A. So it follows that from before, the clean closure of the clean closure of A is equal to the union from k equals 0 to positive infinity of the clean closure of A to the kth power, which we have shown is going to be set containing the empty string union with, and then the union from k equals 1 to positive infinity of, and this is just going to reduce to the clean closure of A. And we see that the clean closure of A union with itself is going to be the clean closure of A, so this is equal to the empty string union with the clean closure of A, which of course is going to be the clean closure of A since the empty string is contained in the clean closure of A, proving that the statement is true. In part E, we're given the statement that the clean closure of A concatenated with A is the clean closure of A. And this is in fact not true. So this is false. And to see why, I want to consider an example A which does not contain the empty string. So let's take, for example, that A is, say, the set containing string 0. Well, then we see that A star contains all strings formed from any sequence of zeros, so that A star is equal to the set of all strings 0 to the n, where n is greater than or equal to 0. This includes the empty string, and therefore it follows that A star A is equal to the set containing all strings 0 to the n, where n is greater than or equal to 1, since we have to include that 0. But then we have that lambda is an A star, but lambda is not in A star A. And so the statement is false in this case. Now, in part F, we're given the statement that the cardinality of A to the n is equal to the cardinality of A to the n. This statement is actually false. So to see why, let's consider a simple counterexample. A equals set containing the strings, the empty string, and 0. Well, we see that the cardinality of A to the first is going to be, well, still going to be the cardinality of A, which is 2, and the cardinality of A to the first is still the cardinality of A, which is 2, so in that case it's correct. But consider cardinality of A squared. So cardinality of A squared, this is going to be the cardinality of the set which contains lambda, 0, and 0, 0, which is equal to 3, while we have that cardinality of A squared, this is going to be 2 squared, which is 4, which is not equal to 3, and therefore the statement is false.